of Networking and Switching Technology at Beijing University of Post and Telecommunication. With the development of container technology, container cloud are widely used as the infrastructure for text execution. The text submitted into cloud have verifying requirements depending on user specific need and expectation. Some texts such as offline data analysis constrained with soft deadline. Failure to meet soft deadline doesn't cause serious consequence, but it may incur penalty costs that the cloud provider need to compensate to user to maximize the benefit of cloud providers. It is critical to allocate the appropriate amount of computing resource to text. Over allocating will result in idle resource, contributing to inefficiency utilization of computational assets in clouds. Conversely, under allocation will slow down the execution of text, potentially incurring penalty. And although the latest approach have shown good results in many aspects, there are some limitations in this approach when dealing with soft deadline constrained text. First, the quota allocation-based approach overlooks the gap between the allocation quota and the actually obtainable amount of CPU time. By default, Linux forces threads from different containers to show all CPU code regardless of their quotas. Containers will most threads will exhaust their CPU quotas earlier in a CPU scheduling period because of their payroll execution in more cores. They will be suspended during the current scheduling period. Second, the co-allocation-based approach lacks a consideration of the dynamic workload change within a decision interval. Some approaches reserve CPU cores to text exclusive, which use the average value to represent the demand on a decision interval. This fails to account for the dynamic nature of CPU usage within the interval. Third, the soft deadline constraint on text further increase the difficulty of dynamic resource management. It is acceptable to complete text after their soft deadline, but the penalty cost will increase as the time period grows. All the above three problems will lead to inefficient CPU resource allocation and increased penalty costs for tasks with soft deadline. To address this issue, they propose a hybrid CPU scaling approach which provides CPU resource for tasks dynamically with the goal of minimizing penalty costs for missing soft deadlines. Next, we are talking about background. Containers have become a popular technology for deploying and managing applications in cloud-based environments. They provide independent virtual execution environment for application on top of the host operation system, containing only necessary libraries and files. Multiple containers can be co-located and sharing computing resources on the same host. The CPU sharing is managed by the Completely Fair Scheduler (CFS), which is the default scheduling policy for Linux and is widely used as an integral part of computing resource management of mass container-based cloud systems. In cloud platforms such as Kubernetes, it is a common practice to use both CPU request and CPU limit to effectively manage CPU consumption of containers. The former specifies the request amount of CPU resource that the container required to execute properly, while the latter is the upper limit to CPU resource the container can use. These values are converted into CPU share and CPU quota to manage CPU scheduling by control group in Linux. And where 1024 is the default constant share wide of one CPU core in Linux, and the CPU period represents a scheduling period, usually 100 microseconds. And the CPU share represents the Y assigned to each application for time slice allocation. When multiple threads share a CPU core, time slices are allocated based on the assigned weight if they need to use the core. If the running time reaches the upper limit, CPU quota, the container will be suspended and cannot be scheduling until the next scheduling period. Next, we are talking about motivating examples. In this session, let's present some examples from which we draw some valuable insights. The gap between the obtainable amount of CPU time and the allocated quota. Assume that two tasks, T and N, are running on a node with two CPU cores. Each thread of these two tasks consumes as much CPU time as possible. Consider a CPU scheduling period. The CPU quotas and straight wires for T and N are illustrated in Table 1, this table. They are allocated with the same quota. Sum the relative value of each thread's weight for these two tasks is inversely proportional to the number of threads. The two threads in text T and denoted as T1 and T2, while the thread in text N is denoted as N1. According to CFS load balancing, the thread of these two tasks may be placed in the CPU core and shown in feature 1, this feature. And T1 is assigned to core 0, and T2 and N1 are assigned to core 1 to show the time sliced according to the thread weight. After about 75% of the scheduling period has passed, T1 and T2 exhaust all the allocated quota of text T. Text T is suspended and its two threads are paused during the current scheduling period. This leads to the idle time of code 0. Unfortunately, this idle time slides inaccessible to thread N1 because it cannot move to the core during this period. And besides, N has only one thread and cannot utilize two cores at the same time. As a result, about 12% of CPU time is wasted. In this case, the total CPU time obtained by N is about 75% of the allocated quota. The gap between the obtainable CPU time and the allocated quota for text N is caused by CFS sharing all cores regardless of the container's quota. If we optimize the core sharing scheme by allocating cores as shown in Figure 1b, text N can obtain the same amount of CPU time as its quota. However, in more complex cases, where the allocated quota isn't an integer, the optimized core allocation scheme may not eliminate this gap completely. Therefore, it is crucial to take this gap into account when making scaling decisions. Dynamic will then change within a decision interval. Assume that we have another two tasks P and Q. The average CPU demand for both tasks during a scaling decision interval is 0.5 cores. The dynamic CPU demands in the interval are shown in Figure 2, this picture. Because the average CPU demand suggests that the total demand of both tasks can be met within a core, we might place both tasks on the CPU cores. However, because of the upward trend in CPU demand for these two tasks, the total demand in earlier period falls below 1 core, while it significantly exceeds the capacity of 1 core later. As a result, the demand of both tasks in the later period cannot be satisfied because they are running on the same CPU core, resulting in performance degradation. Here we are talking about model and problem description. They consider a node with M CPU core in a cloud computing platform execute n tasks with soft deadline. They assume that all other resources except CPU are able to meet the demands, such as memory and network. When text I is submitted to the node at TI0, specified with a deadline TID, and a penalty rate PI to denote the user flexible with delay through compensation. For simplicity, we adopt for linear penalty function as in previous works. When the text I is complete at Ti, the penalty code EI of the text can be calculated by this function, where the notation 0 plus denotation max for any real number Z. The penalty cost remains 0 unless the text missing its deadline. And next, we are talking about problem description. To reduce penalty costs, we need to periodically make appropriate CPU scaling action that can improve the efficiency of CPU resource utilization. In this paper, scaling action include both quota allocation and core allocation for all run tasks. After the all time t, we denote CPU quota of t text I as Qi of t, and use binary variable to represent where text I can run CPU j. And it is also valid solution when the assigned call for text can meet its quota. In this paper, their goal is to minimize the cost for missing deadline, which can be defined as this dimension. And this picture is overview of the IO-based hybrid CPU scaling approach. And features 3 provide an overview of their approach. The IO algorithm used a reward signal to gradually improve the decision policy. And the reward is set based on the high-level scaling object. Example, minimize penalty cost. And look at this picture. And there are three main components, 1, 2, 3. And the quota allocation policy network and the core allocation policy network, which marked as 1, 1, 2, and 3, respectively in this feature. And the text encoder takes final CPU usage series sample within the past decision intervals as input. After prediction and processing through an LSTM, it generates embedded in combined with the text filter. And the embedded in is used to guide the decision-making process of hybrid CPU scaling by the quota allocation and core allocation policy network. These two networks both make decisions based on stochastic policies. In their design, they use an encoder and decoder architecture made up of transformer blocks to process then verifying input and output. For quota allocation, an attention mechanism is used to identify critical tasks that are more likely to incur high penalty costs. And based on an attention distribution, it generates a quota allocation plan according to Gaussian distribution probability. Based on the data collected using a hierarchy-based method, train and bootstrap an initial scaling policy in order to enable the policy network to assess the impact of environment and action on the objective. Based on this model undergoes online training in episodes employing the HPPO algorithm within an actor-critic architecture to handle the action space. And it is essential to consider the dynamic CPU demands of each task and the associated penalty when allocating CPU quotas and code for tasks with soft deadline constraints. To efficiently manage this shared information, they design a shared text encoder that generates a text embedding for each text. The architecture of the text encoder is shown is in Figure 4. And next, we are talking about the rest part of this feature and quarter allocation policy network and co-allocation policy network. And we're talking about quarter allocation policy network. And in this section, let's describe the quarter allocation process for all running tests in the node and the size of both input data and output data vary in size with the number of current running tasks. So they design a quota allocation policy model based on transformer architecture as shown in Figure 5a. And the transformer encoder takes variable length sequence of text embedding Z as input and transform them into encoder represent Z hat represent as this. And the transformer decoder, they then use the initial state along with the encoding represent Z hat to generate decode state D decode decode state DQ, which is represent as yellow block. And since the quota allocated to each text is continuous, quota allocation should be treated as a continuous action. To make quota allocation a stochastic policy, and they model the attention score of each task as a Gaussian distribution following the approach in other works. And therefore, they need to obtain Gaussian distribution parameter, mean and the standard deviation for each text. This is based on the attention mechanism to consider the critical of all running tests and associated penalty cost, allowing optimize the allocation of CPU quota from global perspective. And this can be calculated as follows: 5 and 6. And where W1, W2, and to W6 are learnable parameter. The standard deviation is transformed using exponential function to ensure it remains strictly greater than 0, as required for a very Gaussian distribution. And then normalize the score using softmax function as shown in this softmax function. So the CPU quota Qi assigned to text I is calculated as this function, a function, and where m is the total capacity of the node. And after this, we got a quota allocation decision Q for all running tasks. And let's talk about dynamic workload co-allocation. In this section, they allocate CPU cores for each task rather than sharing a all core without considering allocate quota of tasks. They frame the core allocation as a sequence-to-sequence problem. The input is a sequence that varies with the number of running tasks, and the output is a sequence of task code options. To tackle this, they design a co-allocation policy network based on the transformer pointer network architecture, which is well suited for problems where the output design space is depend on the input. And different CPU code may have varying amount of shared storage, influenced by the CPU topology. In this study, they focus on the NUMA node ID, circuit ID, and fixed CPU ID to capture this topological. To encode this information in code embedding, they utilize the positional encoding mechanism from transformer, and the code embedding has the same dimensionality as the text embedding denoted as DIM. This embedding is divided into three segments, each represent the NUMA node ID, circuit ID, and physical CPU ID, respectively. For code J, the code embedding VJ is encoding as follows: 9 and 10, and where ID represent NUMA node ID, circuit ID, and physical CPU ID, and I is the dimension index. And there are four notation. First is this notation. For a text I and a code J option, they sum the text embedded VI and code embedded VJ to its notation. And then it fed into the transformer encoder to generate code level represent for each text as 12. And output is this notation. And this notation represents the information of code J and text I. And then the code level represent of each text are averaged to obtain the text level hidden state is this notation. And they are fed into another encoder to produce the final text level representation is this notation. And this notation is represent and join text I and the code J. And in the framework of reinforcement learning, the state space and action space are the two most fundamental and core definitions that enable agents to learn. And first, let's talk about state space. In their approach, the state of system at each time t contain the text state and workload state. The text state, which is defined as state t, and they provide information about all running text up to time t. The state space is has many information, and one is the cumulative CPU consumption and the incurred penalty cost and the remaining time to deadline and the penalty rate. In their approach, the state of the system at each time t contain the text state and the workload state. Therefore, the state at time t is defined as this. Next, we're talking about action space. And according to the current state environment, and example according to state t, and the model make a action decision at at the time t, which need to determine how much CPU resource it needs to be allocated to every text and which code can be used by each text. The quota Qi for text I is no more than the count of CPU code, and the relationship of text code Yij is a binary variable. Therefore, the action space is this. We have covered action space and state space. Let's explain how the other process works. The agent observes the state from the environment, and he gather observation, and the agent select an action based on the state. And once the action is taken, a reward function is used to evaluate whether the action was effective. In next reward function, the process of IO enables the agent to maximize the cumulative reward. Therefore, they use the negative of penalty cost in each interval as the reward. As a result, maximizing the cumulative reward corresponding to minimizing the total penalty cost, which is their object. Online learning and model update. Their model online training proceed in episode using actor critic architecture based on HPPO algorithm. The critic estimates the value function, and the actor update the policy in the direction suggested by the critic. Each episode consists of multiple decision events, and each decision event includes a continuous CPU quota allocation action. People can effectively solve this reinforcement learning problem with heterogeneous action space. According HPPO continuous quota allocation policy and discrete quota allocation policy are updated separately for consistency. They denote all of parameter of quota allocation or co-allocation network, etc. Let T be the time step of an episode as a learning run. And the environment information ST is input into the actor network and get the scheduling policy as this notion. And this means is the property of taking action AT instead ST. In HPPO model, learn a policy minimizing the keeping surrogate objective, and the discrete policy and the continuous policy are updated separately by minimizing their respectively surrogate objective. Next, we are going to introduce the experiments. Compare with four approach. Static is statically allocation a fixed quota of CPU resource for each task based on average demand of pre-running. Containerized tasks are allowed to run on all CPU code of the assigned server node, which managed by the CFS in Linux kernel. Second, QAS, a quota allocation-based scaling approach. Third is CAS, a co-allocation-based scaling approach which dynamically allocate code to text based on the static threshold. And that is HHS. And that is HHS. And the result. And for CPU utilization, they measure the utilization of each node are the average result shown in figure 6. And let's look at the figure 6a. Can observe that their approach has an improvement for both the mean and the median CPU utilization. It improved average CPU utilization by over 21% over static and 50% over QAS and 11% of CS. And in figure 7a, they show the reduction in average and median penalty cost of different approach over all runs. And we can see that their approach reduced the penalty cost by over about 24% compared to other approach. And impact on test execution. In the analysis of test execution, they collect and record two key metrics for each test: the execution time and the tardiness. To evaluate the impact of different approach on test execution, they employ cumulative distribution function CDFS in figure 8. An additional table, this table summarizes the relevant statistical data, which help to better understand the test execution performance. By averaging the result across all runs, they generate a plot described in figure 8a. And in table 4, the average execution time of all tasks using their approach is significantly lower, showing a reduction of more than 30% compared to static and 12% compared to QS and more than 5% compared to both CS and HHS. And they also calculate the average execution time for various types of tasks with the result presented in figure 9. and we can see and their approach is the best, and it takes a lowest text execution time. And the feature 10 is show their approach is the lower tardiness. And table 4, this table present the average value, median value, and standard deviation of the relative wait time for different approach compare gains of their approach. The average and median value indicate that test scale by all the other approach experience longer wait time than their approach. And look at this feature. And for each kind of text, they use a bar plot to show relative value and deviation among different rounds for every approach, and overview the result. First, CPU utilization, then increase the CPU utilization, and the approach improve average CPU utilization by over 21% compared on static, 50% compared to QS, and 11% compared to CS. And second is penalty cost. Reduce the cost. The method reduce the penalty cost by over 24% compared to other approach. And the test execution. And the average execution time is significantly lower than the proposal approach, showing a reduce of more than 30 compared to static and 12 compared to QAS. And the CPU scheduling and waiting time. Reduce waiting time. Test managed by static and QS exhibit wait time over 8 times longer than the proposed approach. This indicates that low utilization in other methods often stems from tests being stuck in the ready queue due to the inefficiency culture.